Well, hello, welcome back. We're now going to be transitioning to a different portion of the class. We're going to say goodbye for now to assembly language, and we're going to start thinking a bit more broadly about the computer system and memory in particular. And this is now going to be from chapter 6 of your textbook. So we're going to start by thinking about different kinds of storage technologies and what we mean by memory. So here's sort of an abstract view of your machine. And over here we have our CPU with our registers that we learned about previously when thinking about assembly language. And now we've added this notion of some more memory on board the CPU called cache. And the next few presentations are going to be devoted to thinking carefully about cache. And then we have the other parts of the system, such as main memory, which is connected to the CPU via wires that we call buses. I'll talk a little bit about that later on. And then down below here we have all sorts of input-output devices, such as mice, keyboards, our display that we view things like this presentation on. And also our storage called non-volatile storage, such as disk drives, that does not disappear when we turn the computer off. So one of the big questions and an answer that I want you to realize about what we're going to talk about now is, where is memory on our machine? And we, of course, are first going to say, well, it's over here. It's our main memory. This is what we always say when we have, 8 gigabytes of memory on our machine, or 4 gigabytes, or whatever it happens to be. And so we think about main memory as being the memory on our machine. Now, I'm going to expand that thought for the next few presentations. And what we really want to be thinking about is much more generally, where can we save information? And so we've already seen that we move data from main memory into these registers in the CPU. So there are small amounts of memory on our CPU being saved in order for us to execute instructions. And then I briefly mentioned this notion of cache memories. We're going to talk about these a lot and really try to understand how they work, because they have an effect on the performance of our code. And so we're going to talk a lot about cache memory as also being memory that's in our system and is used when our code is being run. And then, of course, we have way out here this notion of memory that is stored. So we can store programs on hard disk. And this really is just bytes of memory as well. It's the executable programs themselves and big data files that those programs might read in, image files, all sorts of things that we can store on disks that are either built into our laptops or our desktop machines, or possibly even connected wider to the network. So we might even have disks that are off on the network somewhere, out in the cloud. So we really have a lot of different kinds of ways to store data at different points in our computer. And these types of storage, we're just going to think of as memory. Everything is memory. It's a place for that information is stored, whether it's for a short time while the program's running or for a longer time period, such as out here on our disks. And so everything is memory. And this memory now forms a hierarchy. And this is the basic hierarchy that I'm going to go over and talk about some of the elements within this hierarchy. And so what we have here down at the lower end of the hierarchy is what we consider our non-volatile memory. That means that the information is not lost that is stored on them. Now what we are showing here is at level 5 remote storage, so stuff out in the cloud somewhere where information is being stored. And then here at the next level up, these are the local storage on our machines, on our laptops or desktops, or even the disk drives that are on our MSCS1 server. And so these types of storage, the data doesn't get lost. The other thing to note about these types of storage is they typically can hold more data. So that means they're larger here. But they're slower to access than these other types of memory storage. And so that has an effect on how our programs operate. And they're also cheaper per byte, so we can hold more information on these memory storage devices here. And so this is the lower end of this, what we call memory hierarchy. It's bigger because we can typically store more here. And then as we get into the inside of, or the other parts of the machine, these things get much smaller. And these types of memory here are what are called the volatile memory, because only when our program is executing and our machine is on do these memories store information for our particular programs. And so at this level 3, we have main memory, and then we start seeing different levels of cache memory here. Most modern machines have 3 levels of cache. They use a different technology. I'm going to talk about that in a moment for cache than they do for main memory. And then way up at the top here, the fastest memory, but also the smallest and most costly for the CPU manufacturers to create, is the registers right on the machine. And basically, this whole hierarchy in our computer counts on this idea of being able to move data from a lower level up to an upper level. So when we start executing our program, it goes from being stored on some sort of hard drive and putting it in main memory. And then what we're going to start studying is how then data from main memory ends up getting moved into these different levels of cache and is stored there so that it's faster to access by our registers. And so we're going to be looking at this notion of how the cache helps our programs to execute much faster. So that'll be coming up. Let's talk a little bit now about these two different kinds of memory, just a little bit about the hardware that's involved here. So for our volatile memory at the lower end of that picture, at the upper end of the hierarchy, one of the key features of this kind of memory is it's usually multiple little chips, and one cell in these chips holds 1 bit. And so the static RAM, which is used for cache memory, it might look something like this. But in our CPU, it's even smaller. Each cell stores a bit using transistor circuitry. And it can retain its value as long as it's kept powered. So as soon as the machine goes off, it's no longer going to hold the information. It's really fast, but it's expensive, and it uses more power than our standard main memory technology, which is called dynamic RAM or DRAM. And in DRAM, there's a different type of electronics used. A capacitor holds each bit of information, and that actually has to be refreshed every so often, which does make this access of this kind of dynamic memory that's used for main memory slower than the SRAM, static RAM, for cache memory. And it does use less power, which is very helpful because we like our laptops to run for a while. So we typically have more of this in our machines for that reason. Now, these are typically on small boards that are connected into the motherboard of our machine, and they're, of course, larger than these here and hold much more memory than the static RAM does. And we'll see some values of how much static RAM is in typical machines later on in other presentations. Now, the next thing that we want to think about is the non-volatile memories. So those things lower on the memory hierarchy. These are our hard drives or our solid state drives. So these memories, the memories we just talked about, are volatile. They lose information when the machine's powered off. But now our non-volatile memories retain data even if they're powered off. And so they use some way of being able to keep that data around. Now, there's some that we're really not going to talk about very much that are on our motherboards of our machine. Something called PROMs and EPROMs that hold little bits of information. The ones we're going to think about more carefully and talk a little bit more about are these two technologies that most of our disks are made of now. So some disks are made of this, what's called NAND flash memories. And you may have heard the term SSDs, solid state disks. This is one that's put into a server. And then the slowest of our non-volatile memories is the spinning hard disk, which has been around a long time, can hold a lot of information. Now, these non-volatile memories, some of them are used for firmware. So the BIOS you may have heard of. This is a little bit of stuff in our computer that helps it start up in the first place. So we're not going to talk much about that at all anymore. But we are going to mention a little bit about these solid state drives and our spinning hard drives. Solid state drives started out as these little thumb drives, but now actually are being able to be used inside of our computers as disks themselves. Okay, so now the next thing we want to think about is something called the bus. So a bus is a collection of wires that carry the data. So back when we were looking at the assembly language and the move command, we saw how data gets moved from main memory, an address in main memory, and is moved over into some register. Well, this is done at the hardware level via these things called buses. So there's a bus that carries memory over onto something called the system bus, which then puts the data into the register. And so these buses are often shared by multiple devices. So I'm not showing the whole system here. Here now is the whole system with the other devices that are all connected. So there's typically some sort of a bridging and data can get moved on these various wires. Now you've probably often heard about your CPU having a particular clock frequency. And the faster that is, so the more instructions that it can execute in a second, which is typically a lot, that's one thing we think about as far as how fast our machine is. But I'm going to argue with you that the data transfer rate, so the amount of time that it takes for data to go across these buses, is actually the more important aspect of our computer in terms of how well it is going to perform. And so we're going to start trying to think more about this notion of how many bytes per second can get moved from main memory over to a register and so on. And so the speed of what's going on inside here in our computer can often be the most deciding factor on its performance. So what are these buses really like? Here is a photo of a small motherboard. Now, right here is where that CPU would be. So our CPU here, it would be placed right here on the motherboard. This part, you see, it's pointing to something called a bus controller. That's kind of this area here, all these different ways of controlling the data. So this bus controller is similar to this I/O bridge here. And then here you'll notice, here's where the DRAM slots are. So this is where those the memory would be placed on this particular motherboard. And this little BIOS ROM, that's one of these memories that holds a little bit of information for the BIOS. And then there are all of our I/O connectors over here for the mouse and for this one's kind of old. It only has a VGA connector for the graphics. So now this is a somewhat typical setup for a small one of these motherboards. And now if we were to turn this thing over, you might see a little bit, let me go back one second, you might see a little bit here, some lines here. These are kind of the most prominent that you can sort of see. There's a few over here. But if we were to turn this board over, this is more like what the back of it is. So the CPU is going to get placed on the other side of this board right here. And then we have these really many different wires that are going out of here from down in this area and go over to places like where the main memory is and where the disk is and so on. And so all these wires make up the way that bits get moved between these various pieces of our hardware. So these things we call buses really are these crazy wires that we see on the back of this particular motherboard. And so the wires are the buses that carry the data and the signals. Now it's kind of interesting. We want to think a little bit about how this works since all of these are connected to the bus. We want to think about how this all works. So data moves across these wires in a particular way with this kind of rhythm in a set of steps. And I want to talk a little bit about this. And your textbook goes into this for several examples. I'm just going to pick one example. So suppose that in a part of our program that's running, we want to read some data from the disk. What really happens here in this process and rhythm that goes on is that the CPU first sends a command saying, hey, I know what part of the disk I want to grab the data from. And it also sends over a memory address. Where in main memory should this data that we're going to read from the disk go? And so the CPU issues this disk read by writing a command onto the bus. And then the disk controller says, oh, okay, I got your disk read command. Let me grab that data from the disk, and then I'm going to move it over into main memory. Now, the disk controller does that and uses the bus to do that and really takes control of the bus at that point. And so the disk controller then really has to let the CPU know when that data has been fully transferred. And so that's the next step, is that the disk controller goes back and sends something called an interrupt signal to the CPU saying, hey, it's done, your data is in memory now. And so this is what I mean by the different kind of a rhythm of the machine. There's a request, the action takes place, and then an interrupt is sent saying, okay, I did it, it's done. And that's sort of the way that all these things use this bus, is through this process of asking for something, doing it, and then sending an interrupt saying, hey, I did it. So that's just one example. There are plenty of examples very similar for using all of these other devices as well. Now, this particular action takes some time. And the main reason that it takes a fair amount of time is because if this was being done on hardware like this technology, there is a lot of what we call latency. So once the CPU asks to go read from this disk, basically this arm has to move to the right place on the disk. The disk is spinning very fast, and it has to wait until the right area on the disk is underneath this arm, and then finally it can start reading. And so this takes a lot of time. These disks are made up of this magnetic material called platters, and it takes some time to read this information. And so this is why this is one of the slower technologies. And so one of the things that's worth thinking about is the transfer rate of this information. And in this particular case with this technology, the time it takes to move the arm to the right location and wait for the disk to spin is called latency time. That affects the throughput. It affects how many, say, megabytes per second or gigabytes per second we can move data across that bus. And that leads to what we think of as an overall access time as well. So how long is it going to take to move a certain number of bytes that we've asked for? And so this is how we want to measure the performance of different parts of the memory hierarchy. And I'm mentioning the hard drive at the bottom because it's the slowest one by far. So the latency of something like that hard drive plays a big role in how well our machine is going to work. And we're going to see ways that the machine is able to sort of compensate for some of this latency. And it's one of the reasons, the latency of hard drive storage is one of the reasons that we now have started using these solid state drives and this NAND flash technology, because it is much faster to access. So here's a couple of examples of these solid state drives. This is one you would put inside of a server. This is one that's got a case, so it might be an external drive of some kind. Now these drives, they really are a lot faster because they don't have all this moving hardware that takes so long to access. And so you get a lot less latency. You don't have the moving heads and rotating platters. You can get at every piece of data at the same amount of time. Reading and writing do have different times, different speeds in this technology. I'll show you an example of that. But the quicker response of this kind of technology really means that we can have faster access and the throughput in general over that bus. So the amount of bytes per second that we can move tends to be faster using this new technology. So here's some performance characteristics to compare these. So with our solid state drives, notice here that a random access of data is on the order of 30 microseconds, whereas for a hard drive, it's 14 milliseconds. So this is a big difference between 10 to the minus 3 and 10 to the minus 6 here. And so this is why this technology is quite a bit faster. And it is kind of interesting the way they designed this stuff. They designed it so that writing does take longer than reading because there's more, you have to change what's stored in the circuitry. But it's still considerably faster than writing to our spinning hard drives. So then, why aren't we just, totally going to using solid state drives? We may at some point, but let's think about it a little bit. So the solid state drives have no moving parts. So they're faster, they use less power, and they can be much more rugged. It's nice to have them in your laptop and if you carry it around a lot. Now, the disadvantages is that at some point, these have a tendency to wear out, although that's getting a lot better in in recent times. But the big thing is that we still can get a lot more capacity on one of these spinning hard drives than on one of these solid state drives. So that's the main driver behind still using hard drives a lot for data storage. Now, another disadvantage that's dwindling is it used to be that SSDs were far more expensive per byte. But over the last 5 years or so, this is getting very interesting, especially at least for the cheaper types of solid state drives. The price per byte is evening out down here. You still can hold a lot more on a spinning disk drive, but the price per byte that you pay has become equal, at least to some of the cheaper SSDs. So that's quite interesting. And so, we may see at some point the end of the spinning hard drive, but not until we can get far more capacity on our SSDs. All right, so now to kind of wrap this up, I want to remind you again about this memory hierarchy and how it relates to this abstract view of our computer. So here at this very lowest level, the slowest access is really stuff out on the network in the cloud. That's going to be our slowest, but also our biggest source of data in terms of number of bytes. And then next on the hierarchy is our spinning hard drives. And those are further away from the CPU, not quite as far as out on the network. But that too is the reason that the throughput here is slower, not only because it spins, but also because we have to move data all the way through the bus here. Next up from that is our newer technology, our solid state disk drives. And those have less latency, of course, so the data movement is faster here across the bus. And then our main memory inside of our machine, our DRAM technology, that, of course, is closer to the CPU, and therefore the movement of this data is faster. Yet, there's, of course, less of this than on the other levels of the hierarchy, and so that's there's only so much we can store in the main memory of our machine when we're executing anything. And then after that comes these levels of cache, and so this is the green stuff here. And of course, these are on the CPU, so they're going to be faster access, and that's why they're higher up on this hierarchy. We're talking typically in the order of 32 to 64 kilobytes only of data here at this level. And then our small registers, and you saw how many of those there were, not very many at all, right, on our Intel CPUs. And so that's the fastest access for for instructions to be able to execute, but there's very little of it. And so what we're going to see as we move forward here is how do we take advantage of this cache and its interplay with our main memory in order to make our programs as effective as we possibly can. So stay tuned for that coming up.